In this lecture, we talk about simultaneous linear equation, SLE. That is a big topic. And in specific, for this particular lecture, we talk about how to solve simultaneous linear equation by using Cholesky method. Okay, let me start with lecture number 23 on the topic solving simultaneous linear equation by Cholesky method. In this topic, we would like to solve the system of linear equation shown in equation 1 that can be represented in the matrix notation as AX equal to B. In equation 1, the matrix A is called the known coefficient matrix, and it is the square matrix with the dimension n by n. It is a known matrix. The vector B is a known right-hand side vector, and the dimension is an n by 1. And the vector X is the unknown vector, which has the dimension n by 1. So basically, in this equation 1, for a given matrix A and for a given vector right-hand side vector B, we want to solve for the unknown vector X. That's what we want to do. Now, we make the assumption that assuming the matrix A is symmetric positive definite. I will explain to you in the next few slides what do I mean by symmetric positive definite. But in order to make the Cholesky method working, we have to make the assumption that the matrix A right here has to be symmetric and positive definite. So assuming that criteria is satisfied, then according to equation 2, we would like to factorize or decompose the matrix A into a product of matrix U transpose times the matrix U, where the matrix U is defined as an upper triangular matrix, as you can see from equation 3, like that. And therefore, the transpose of the matrix U will be something look like a lower triangular matrix right there. So if we assume the matrix A is symmetric positive definite, and it is known, it's given, the question becomes, how do we figure out the matrix U, which is the upper triangular matrix, that we call it the factorized matrix U? How do we find the factorized matrix U? Well, the answer is very simple, because if you look at equation 3, all we have to do is to multiply both of the matrices on the right-hand side. And after you multiply both sides of the matrix on the right-hand side, basically you will get a 3 by 3 matrix. Symbolically, it can be represented like this, a 3 by 3 matrix. Okay? And then after that, we just equated each term on the right-hand side of the matrix with the left-hand side. For example, we will equate this term with A11. We will equate the rest of the term, let's say here, with the corresponding term on the left side of the equation. So the procedure is very straightforward. All we have to do is just multiply these two matrices, and the result will be a 3 by 3 matrix like that. And then we just have to equate the upper triangular portion of that matrix corresponding to the upper triangular portion of the left-hand side. Then we will get 6 equations. And from those 6 equations, we should be able to solve for the 6 unknown: U11, U12, U13, U22, U23, and U33. The reason I say we want to do it row by row factorization is because we want to do the computation of the matrix U of the factorized matrix U according to the order row 1 first, then we do it for row 2, and then we do it for row 3. And that's why we call it row by row matrix factorization. So at the end of the step number 1, we should be able to calculate the matrix U. As you can see from the next slide, and you compare to the previous slide, after you equate the upper triangular of the right-hand side with the upper triangular of the left-hand side, term by terms, we will get 6 equations. And those equations is shown right here as equation 4 and equation 5. You can see we get 6 equations. The first equation can help us to solve for the term U11. The second equation helps us to solve for the term U12. The third equation helps us to solve U13. So basically, these 3 equations will help us to find out the factorize of the first row of the factorized matrix U. And similarly, we have the fourth equation to figure out U22. The next equation will figure out U23, and that will take care of the second row of the matrix U. And finally, this last equation here will help us to figure out the third row of the matrix U. As you can see from the Cholesky operation here, because we do have the square root operation involved. We do have the square root operation involved. This is square root operation involved. And that's why we want to make sure that the matrix A has to be symmetric positive definite. And in the next few slides, I will explain to you more about what do I mean by symmetric positive definite. Okay, so at this moment, we already figure out all the term in the matrix U, the factorized matrix U. Well, what happens if the matrix dimension is bigger than 3 by 3? For example, it could be a 4 by 4, 5 by 5, or 10 by 10, or bigger. Well, using the same idea, mathematicians already developed a general formula such as equation 6 will help us to figure out all the diagonal term of the matrix U. And we can also figure out by using equation 7 to find out all the off-diagonal term of the factorized matrix U. So for any matrix with any dimension, we can factorize row by row again according to equation 6 or equation 7, depending on you want to factorize the diagonal term or the off-diagonal term. Now, if you take a little bit closer to equation 6 and 7, you will see that the denominator of equation 7, the denominator, turn out to be the same thing as the term under the square root of equation 6. They are the same if the index I is the same thing as the index j, then the two are the same. As you can see, aij become aii, uki times ukj become uki square. So what does that mean? So what it means is we have to figure out the denominator of equation 7 first, which is this thing in here. And after we figure out the denominator of equation 7, we just make an if check. If we want to calculate the diagonal term, then all we have to do is just take the denominator here and take the square root. Otherwise, we just take the denominator that we just calculated and then divide by uii. So in other words, what I'm trying to tell you is that equation 6 and equation 7 basically among the two equations, equation 7 is more important. Now notice one thing. There's another thing that I want to mention also in here. There's another thing I want to mention also in here. Suppose in the beginning, let's say the value of aij right here is equal to 0, let's say, assuming, okay, is an example. Assuming aij equal to 0. Well, in that case then, the value of uij could be 0 or non-zero depending on this summation of the product. If this summation, if it is 0, then this term uij is also equal to 0. On the other hand, if this summation is not equal to 0, then even though the original value aij is 0, but the factorized term uij will not be equal to 0. So when you have a situation where the original value of aij is 0, but uij term is not 0, then we say we have the so-called fill-in term. Fill-in term. And later on we will see I use the symbol capital F to represent it is a non-zero fill-in terms during the factorization process. So let's take a look at a quick example so that it will help us to understand how to use the equation 6 and equation 7 in order to find out the factorized matrix, okay? So if you take a look carefully in equation 7, for example, take a look at equation 7. So if you take a look at equation 7, suppose I want to calculate what is the value of U57. I want to calculate it. So basically it means I is equal to 5 and j is equal to 7. So if I equal to 5, that means this summation I minus 1 will be equal to 4. Okay? So directly apply equation 7, then you will see U57 equal to A57 minus the summation of the product shown in equation 7, and that is right there. That is the summation shown in the equation 7. And then divide by U55. Divide by U55. Now, if you observe that equation, you can see very clearly that in order to calculate the factorized term, a particular term such as U57, all we have to do is to refer to column 5, column 7, column 5, column 7, column 5, column 7, column 5, column 7 of the term that you already factorized. That is the main idea. So either you can refer to equation 6 or 7